Hi, so today we're going to continue our Unit 8, our Section 2 of Chapter 12, which is our chi-squared test for homogeneity. Today our learning targets is pretty much, we're going to do the four-step process on the inference method, the chi-squared test for homogeneity. So the chi-squared test for homogeneity is a significance test of the null hypothesis that there is no difference in the distribution of a categorical variable in the populations of interest or for the treatments in an experiment. So pretty much you're comparing several test groups or populations to see if they have the same distribution for a categorical variable. That's the difference from the chi-squared goodness of fit. So looking at this problem, it says, does background music influence what customers buy? One experiment in a European restaurant compared 3 randomly assigned treatments: no music, French accordion music, and Italian string music. Under each condition, the researchers recorded the number of customers who ordered French, Italian, and other entries. So our null hypothesis here is going to be there is no difference in the true distribution of entries ordered at this restaurant when no music, French accordion music, or Italian string music is played. Now, our alternative is that there is a difference in the true distribution of entry orders at this restaurant when no music, French accordion music, or Italian string music is played. Now, you do need to be cautioned that the alternative hypothesis does not state that each distribution is different from each of the others. So they give us their data both in a table and the graphs here for how many entries were ordered depending if there was music or no music and the type of music. So does the difference in this distribution provide evidence, convincing evidence, that background music affects customers' behavior at this restaurant? Or is it plausible that the background music has no effect on customer behavior and that these differences are due to the chance involved in the random assignment of treatments? So we could compare many pairs of proportions, ending up with many tests and many p-values. But this is kind of a bad idea. When we perform multiple tests on the same data, it does increase the probability that we make a type 1 error in at least one of the tests. So how can we avoid this? So the problem of how to do many comparisons at once without increasing that overall probability of a type 1 error is a common in statistics. So there are statistical methods for dealing with multiple comparisons. They usually have 2 steps, which is our 4-step process, right? To perform an overall test to see if there is convincing evidence of any difference among the parameters that we want to compare. And then our second is when the overall test shows that there is convincing evidence of a difference, then we perform a more detailed follow-up analysis to decide which of the parameters differs and to estimate how large the differences are. So going back to this one, just like we did with the chi-squared, goodness of fit, now that we're looking at the test for homogeneity, to find our expected values, notice that we do have different categories. We have French with a total of 99, but none here, 84. So we do have multiple information. So to find out our expected value, if we just look at, for instance, the French entries, for this particular specific type of music, the proportion for French entries ordered under each of these music conditions would be 99 out of 243. Now, we do need to take into account some other things, which is the 84 total entries ordered when no music was playing. So the expected count would actually be 84 times 99, and then we divide it by 243, which is 34.22 of those entries to be French on average. And that's how we're going to actually find our calculating our expected count. And this chart here, if you notice, this is our expected count. So we have our observed table that we just saw, and now we have what's called our expected counts. And we do want to make sure that we write all this down. So our expected count, if we look at it, it is to find that expected count, we're going to multiply the row times the column divided by the total. And that's how we find the expected count for each of them. So for the Italian, we would do the Italian row, which is 31, times the column, and then times the total. And that's how we get this one here. Okay, to get to the next one, we do this one, 99, times 75 divided by the total. So it's the row times the column divided by the total. So as with the chi-square test for goodness of fit, the expected counts should not be rounded to the nearest whole number. While an observed count of entries ordered must be a whole number, an expected count need not be a whole number. The expected count gives the average number of entries ordered if the null is true and the random assignment process is repeated many, many times. So just like the chi-square goodness of fit, to find our chi-square test statistic is going to be the same. We have to find the sum of the observed account minus the expected count squared divided by the expected account. So we're going to do the same thing. So we're finding the sum of the overall cells, not including the totals, in that two-way table. So we're going to do 30 minus 34.22 squared divided by 34.22. Remember, we put the first two plus ... and then the last one. And then we can go ahead and do that calculation. So our chi-squared here is 18.28. Now, of course, I am going to show you how to use the calculator in a bit to kind of simplify our work. But remember, I always want to see this part because if not, you might get deducted a little bit of points if you messed up putting some of your information into your calculator. So I do want to see this part here. So in the do step, you aren't required to show every term in the chi-square test. Writing the first few terms of the sum followed by ... is considered as showing work. So make sure that you do this and then let your calculator tackle those computations. So let's look at this problem. So it says, for a class project, Abby and Mia wanted to know if the gender of an interviewer could affect the responses to a survey question. The subjects in their experiment were 100 males from their school. Half of the males were randomly assigned to be asked, would you vote for a female president? By a female interviewer. The other half of the males were asked the same question, but by a male interviewer. The table shows the result. And these are our three questions. So the first question is to state the appropriate null and alternative hypothesis. So with this first question, with part A, remember that our null means that there is no difference. Okay, so there is no difference in the true distribution of response to this question when asked by a male interviewer and when asked by a female interviewer for subjects like these. The alternative is that there is a difference in the true distribution of responses to this question when asked by a male interviewer and when asked by a female interviewer for subjects like these. Moving on to part B, showing the calculations for the expected count in the male yes column, then provide a complete table of expected counts. So we need to do this table, which is the observed, and we do need to get our expected table. So remember, to get our expected for the male yes, we multiply the row, which is 69, times the column of the male, which is 50, divided by the total, which is 100, and that's how we get that 34.5. The rest of the expected counts are shown on the table, so you can go ahead and do the rest of those. Then part C says calculate the value of the chi-squared statistic. So we're going to do the first two, so 30 minus 34.5 squared over 34.5 plus the next one, plus dot, dot, dot. And then we do the last one, which is 8 minus 10 squared divided by 10. And notice that I went to 30, and then I went to 39. And then the last one that I wrote was this one. And that would give us 4.25 for our chi-squared test statistic. Now, just like the other ones, our conditions for performing a chi-squared test for homogeneity is the same. We need to check our random, we need to check our 10% condition, and because this is a chi-squared, we do need to show that all expected counts are at least 5. So we do need to make sure to show that table and label it expected count so that you can get full credit. Don't just make a table without labeling it that was your expected count. So looking at this next problem, it says the preceding example, you read about an experiment to determine if the gender of an interviewer affects responses to the question. Would you vote for a female president? Here are the tables showing the observed and expected counts. Earlier, we just calculated that the chi-squared test statistic was 4.25. Verify the conditions for the inference. That's our first question. So we're going to check the random. The treatments were randomly assigned. Perfect, check mark. Then notice that we don't need to check the 10% condition because Abby and Mia didn't randomly select subjects from some population. So we didn't have to check the 10%. Now the large count, we do need to show that all expected counts is greater than or equal to 5. And notice that we have to put see table of expected count. So you do need to make sure to give me that table so that you can then refer to it. Part B, use the table C to find the p-value, then use your calculator's chi-squared CDF command. So here are degrees of freedom. Now, notice that the degrees of freedom are a little bit different. We are going to do 3 minus 1, because it is our rows minus 1, times our columns minus 1. And that's going to be our degrees of freedom. So it is very different than the chi-squared goodness of fit. So again, it is the rows minus 1 times the columns minus 1. So here, the p-value for degrees of freedom is between 0.10 and 0.15. Now remember, I don't like using table C because, again, it doesn't give us our exact value here. Now, if we use our technology, that's a little bit better. So our chi-squared CDF, our lower would be 4.25 because remember, we're talking about a chi-squared. It is skewed right, and we're shading to the right. So our upper, we can say 10,000, 9E999, we need to use a large number. Degrees of freedom is 2, and it's 0.119. That would be our p-value. Now we need to make sure to interpret the p-value from the calculator. Remember, this is not necessarily used on the FRQ, but they will ask it on the MCQ. So you do need to understand what the p-value means. So assuming that the gender of the interviewer doesn't affect responses to this question, there is a 0.119 probability of observing differences in the distribution of responses as large as or larger than those in this study by chance alone. And we've been interpreting p-value quite often. And it's the same type of interpretation for all. D, what is the conclusion we would draw? So here, our alpha level is going to be 0.05 because they didn't specify it. So because our p-value of 0.119 is greater than our alpha, which is equal to 0.05, we fail to reject the null. There is not convincing evidence of a difference in the true distribution of response to this question when asked by a male interviewer and when asked by a female interviewer for subjects like these. Now, of course, we can use our calculator to simplify a lot of this work for us. So in our TI Inspire, we're going to go to matrix and vectors because we are looking at a table. So we're going to go to matrix and vectors. We're going to create a matrix, and this was a 3 by 3, and we're going to input our data. Once we input our data there, we're going to go to statistic, stat test. This is going to be a chi-squared two-way test. And we're going to click A. Make sure that when you input your matrix, you store it as A, and I'll show you how to do that in class. And then notice it does give us everything that we need. So we do get our chi-squared statistic, which is, notice, the same thing that we got, our p-value, and it does give us our degrees of freedom if we're looking at that very first problem that we were looking at. You can see that your calculator does carry out the mechanics of the significance test on the AP statistics exam, but there is a risk involved. If you just give the calculator answer without showing any work, and one or more of your entries that you inputted is incorrect, you will likely get no credit for the do step. So I would recommend for sure writing out the first few terms for the chi-squared calculation. So remember the first two plus ... and then the last one. And this approach may actually help you earn some credit, so some partial credit, if you enter a number incorrectly. And then be sure to name the procedure. Always name the procedure because that does give you points. And to report what the chi-squared statistic is. So don't just give me this number. You got to tell me what it's equal to. Give me what the degrees of freedom is. And then, of course, tell me what the p-value is. And again, our chi-squared test for homogeneity, our chi-squared test statistic is found by the sum of the observed account minus the expected account squared divided by the expected account. And then the degrees of freedom, it's the number of rows minus 1 times the number of columns minus 1. So that's very important because that is very different than the previous degrees of freedoms that we've done. Let's look at this next problem. It says, the Pew Research Center conducts surveys about a variety of topics in many different countries. In one survey, it wanted to investigate how residents of different countries feel about the importance of speaking the national language. Separate random samples of residents of Australia, the United Kingdom, and the United States were asked many questions, including the following. Some people say that the following things are important for being truly, and then the surveyed country nationality. Others say they are not important. How important do you think it is to be able to speak English? The two-way table summarizes the response to this question. Does this data provide convincing evidence at the alpha of 0.05 level that the distribution of opinions about speaking English differ from residents of Australia, the UK, and the US? So here they're giving us the observed table for all the different questions. So what we're going to do is we're going to do the four-step process to solve this. So we're going to first state what our null is. There is no difference in the true distribution of opinion about speaking English for residents of Australia, the UK, and the US. And the alternative is going to be that there is a difference in the true distribution of opinions about speaking English for residents of Australia, the UK, and the US. And of course, here you do need to give me the alpha level of 0.05 because we are doing the four-step process. Now we're going to move on to the plan section. The first thing that you have to give me is the inference method that you are using. So in this one, we are doing a chi-squared test for homogeneity. So once we stated the inference method, we now check our conditions. So random, it's an independent random sample of residents from the 3 countries, okay? I would actually be more specific and not just say 3 countries. I would say actually Australia, UK, and US. Then the 10% condition, I would say here we have 1,000 is less than 10% of all Australian residents. 1,460 is 10% of all UK residents, and 1,003 is less than 10% of all US residents. And then the large counts, all expected counts are greater than or equal to 5. And of course, we're going to use the table And then here's our table. Notice that we labeled the expected counts and we did row times column divided by the total, and that's how we got this one. And we keep doing it for the other ones. Okay, we're going to move on to the do section. So we do need to find our test statistic, which is chi-squared is equal to. Remember, you got to give me the first two plus ... You should give me the last one here. I think it got eliminated, but it should be the last one here. And you get 68.57. The degrees of freedom, it is the row, there's 4 rows, minus 1, 3 columns, minus 1, and then multiply and you get 6. And we're going to use our technology. So chi-squared CDF, the lower is 68.57. Our upper is 9E9999. Degrees of freedom is 6. And this is a very, very, very small number. So it's approximately 0. Now to conclude, because a p-value of approximately 0 is less than the alpha, which is 0.05, we reject the null. There is convincing evidence that there is a difference in the true distributions of opinion about speaking English for residents of Australia, the UK, and the US. So many students lose credit on the AP statistics exam because they don't write down and label the expected counts in their response. It isn't enough just to claim that all expected counts are at least 5. You must provide clear evidence. So you must show that table and label it expected count. And this was our learning targets for 12.2. We're almost there to finishing up. Great job.